So we're trying to compare the solar cell between this resistor here, which has 650 ohms, and this resistor, which has 1300 ohms. When we connect this together, we'll get a voltage difference across this solar cell of 0.3, and this one has 0.23. This is trying to set up like a real situation where we're going to have an internal resistance. And so we're asked to figure out what those two components are. Well, we should know that there's going to be two different currents in this situation. So we'll call this one I1 and this one like I2. And we just got to kind of figure out which direction it goes. It should come out this direction. So like that. All right. Now we can set up a couple of different ideas. First off, we should remember that if we're trying to get the voltage for a real battery, it's going to be like epsilon minus IR. And that would be I1. And then over here, we would do I2. And we kind of actually would be able to know what that I is because we also know Ohm's law. Ohm's law says that V equals IR. And so therefore, if you just divide V by R, you'll get the I. And that's what we'll do right here. So we kind of get like 0.23 volts equals epsilon minus 0.23 volts divided by 650. And then times the internal resistance. And we'll do the same thing over here. It's got 0.3 on top and 1300 on the bottom. And then if you just move these things on the other side, you'll notice that epsilon will just be remaining there. And so you can kind of go 0.23 plus 0.23 over 650 is going to be equal to 0.3 plus this one here. That's like that, and then R. And that's cool. We could even try multiplying everything by 1300 to just kind of even things out over here. We do that. We get 1300 times 0.23, 299 on this one. Plus, this was going to turn out to be like a 2 times 0.23, so that would be 0.46. That'll be an R there. And that's going to be equal to 1300 times 0.3, 390. And then plus 0.3. Should be able to get this one pretty easily if we just subtract 299 on that side. We would get 91. And then that'll equal 0.16. All right. So 91 divided by 0.16 should get that the internal resistance is 568.75. All right, so that's good. And then we could just plug it right into this equation over here, and we'll basically see that you'd have like 0.3 is equal to epsilon minus 0.3 over 1300 times 568.75. And so you can kind of say like, okay, 0.3 plus 0.3 divided by 1300 times 568.75. And that should give us the epsilon of this, the EMF, is 0.43125. And okay, so this is good. So we've got those two, and now we're looking at the efficiency. And the efficiency is trying to say we got these two things here. We're trying to compare if the light energy comes in. Here's the light energy, and then we have our little resistor here, and then or our little circuit here. This is our circuit, right? And on the other side, we have this because it's going to go into like the solar panel over here, and then here's going to be your resistor, but the resistor is going to pump out some heat. And we're going to ask ourselves, okay, how much light did we get? It's a big amount of light, and then how much heat did we put out? That's the question. How much heat did we put out? So in order to do that, let's remember what the equation was for the heat dissipation. It's supposed to be P equals V squared over R. So let's try to do that over here, I guess. V squared over R is going to be 0.3 squared divided by the resistance. I guess we'll do it on this side. So 0.3 squared divided by resistance. So 1300. So we get this really small number. Try to mark that over here as the heat was 690. 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6, 69.2. And this is going to be microwatts, because this is heat. And then we're going to try to figure out how much light came in. It says that the rate of energy per area, we're given these two numbers. Milliwatts divided by centimeter squared, and then the centimeter squared over here. My guess is we're going to just try to multiply these together, which makes sense. So that way you'll get a total energy output out of that. So 5 e to the negative 3 times 1.3. Because it's 6.5. So this is like the light energy was 6.5 milliwatts. And we ask ourselves, all right, which one's bigger? Which one should go on the bottom, I guess? What's the efficiency formula? It's output divided by input. And times 100 and stuff. But that's essentially what we're comparing. Well, the output was this, and the input was that. So we're going to divide that by that. And if we do that, we would get 69.2 e to the negative 6. Divide that by 6.5 to the negative third. And we'll multiply that by 100. So that way we get 1.06%. 1.06%. So that's an incredibly low efficiency rate, but that's what we're looking at there. You could think of it as kind of like a massive amount of light comes in and a really small amount of heat comes out, because we got milliwatts coming in and then 1,000 times smaller amount of heat coming out. It's crazy.